So I promised you some exciting tech talk before this was all done today. And we're thrilled to have Sandy Pentland with us, who's going to tell us, not just in healthcare, but also his experiences in, as you've read his bio on here, a variety of serial entrepreneur, extraordinary academic achievement, and just fun. Sandy, thank you so much for being with us and talking about this. You can stand up here, down there, wherever you would like.
Okay, good. So now I got to be fun. This is I got to wake up, right? Yeah, all that. So I'm going to talk about work we do at MIT under the name Trust Data Consortium. And what it is something that comes out of a lot of years of experience that I've had in just how screwed up the data environment is, basically. Okay? So, there's all these privacy questions in the world, and there's all the cyber attacks. And of course, in health, one of the big things is that people can't share data because it's patient data. They can't share data because it's proprietary. It's the wrong type of data. How do you get around all these things? And I think that there's a couple of very basic principles that are at the root of all of this. And fortunately, you don't have to reinvent everything to get it right. And there's even an existence proof of this on a smallish, couple million person scale. And so I'm going to tell you a little bit about that. And you can sort of say, God, if those guys can do it, maybe we could too. Well, maybe not. We'll find out. So I do a lot of different things, and you could ask me questions about a lot of stuff if you're interested. I'm on the board of directors for the Global Partnership for Sustainable Development. I'm an advisory board for the American Bar Association. This should make you nervous. Secretary General, and also boards for Google, AT&T, the city of Beijing, and others. Anyway, so I want to start with this because I figured you guys would fall asleep otherwise. Tech talk, what's that? So this is from the CTO of the US Department of Health and Human Services. Said in email, holy shit, the implications for healthcare are enormous. So maybe he's right. So pay attention and we'll see. And do any of you have sort of a legal background? No? Okay, so the reason is not the normal sort of thing that you would think of as a computer science thing. It's a legal thing. And that is what I'm going to tell you makes it possible to use data without, and get answers without owning the data, without violating locality things, sort of, moving it out of country, without violating privacy things, or for instance, HIPAA. And that's really radical. I mean, just imagine that all data was available to you. And what this does is it makes all data legally available for certain classes of questions. And it's a large class of questions. Okay, so that's the thing. It's like, wow. So the way we think about things is wrong in this framework. Okay, so it's called Open Algorithms, and it addresses a number of concerns. The idea is that you want to have a system that is as transparent as possible. So we're talking about bias in data and bad sampling and so forth. You really want to be able to look at the algorithms that are being applied to the data in order to tell if this is doing what you really think it's doing, okay? So a lot of times, people take data and they do magic things to it and they come back with an answer, and you have no bloody idea whether it's biased, whether it's how true it is. You have to trust them. In cryptography, nobody ever does that because they've learned the hard way. Many eyes makes algorithms, data, et cetera, better. So what they do is they always publish the cryptography algorithms, the actual code, right? And you think, wow, that's pretty weird. Here's this stuff that's like for secrecy, right? And they're making it open. And the reason is that I continually find bugs in it years later, even for some of the best developed things. So Open Algorithms is the name of it. And it has a number of characteristics. So one characteristic is that when we think about data as humans, the first thing that we do is, well, we'll get all the data and we'll stick it here, and you've already made a very bad mistake. Because very, very few things require all the data to be in one spot. Effectively, nothing you can specify beforehand relies having all the data in one spot. And the moment you put it in one spot, first of all, you've just spent your gross national budget on lawyers to try and get deals to get all the data in one spot. You've taken on liability, and you've told the bad guys where to go, right? And once they get in, they've got everything, because all the data is there. This is dumb, but we all do it, okay? To just give you a sense of dumb, right? So imagine that you're a military commander, right? And you have all these troops and stuff, and you say, well, what I'm going to do with my troops, I'm going to put them all in one spot with a wall around them, and then they'll be safe, right? And that's what they did in the 1300s and 1400s. And by the 1500s, they figured out this was a dumb idea. Because the moment you stick everyone in one place, the bad guys know where to go, and somebody on the inside sells you out, maybe accidentally, maybe purposely. In cybercrime, something like 70% of the successful attacks are insider attacks. The majority of those are not actually attacks. They're just people doing stupid things like bad passwords and stuff like that. But the point is that you are going to lose the battle occasionally. People will attack it. They will steal your data. It doesn't matter what you do, okay? And what you want to have is defense in depth, right? So if the data is all in one spot, you lose everything. If the data stays where it's collected, for instance, in heterogeneous systems, then they have to attack each one at a time with a different sort of attack. They're not going to get everything. So that's the first principle. So what do you do, actually? Well, what you do as a data system is called a federated data system. So if you collect data over here and you collect the data over there, what you do is you send questions to the data, and it's executed locally, and then the answer comes back. And of course, the question and the answer are encrypted in various ways. But the point is you don't make copies of the data, and you're keeping it federated, which means it has defense in depth. Okay? Why does this matter? Well, it matters because data collected in one place may have, in the terms and conditions, the ability to do research on it, but it typically does not have the ability to be shared with somebody else. If I own data and that's my business, I may be willing to answer questions about the statistics of the data because it's not something that affects my business, or I may want to know the answer. But I'm not going to give you the raw data because then I'm out of business. So it's hugely easier to set up question and answering systems, and much, much safer than sticking everything in one spot. Well, this sounds like sort of, maybe you guys are saying, this is really dumb. But if you look at what people actually do, they all stick the data in one spot. Bad. Log everything. One of the things that you find when you actually look at what people do is they mess around with the data. You don't know exactly what questions were asked. You don't know exactly what algorithms are run on it. Maybe there were 2 or 3 answers, and you took the one you liked. Or, so to have a system that's actually safe and a system that you can audit, which is legally very important, you have to log things. And we have these things called blockchains. Everybody knows them now because of Bitcoin. That's not the blockchain we're talking about. Don't use that. But there are ones that are very efficient. And the example that I'll give you a little later is the country of Estonia has been logging all of its state data, all of its medical data on a blockchain for 20 years. It just works. Right? It's not complicated. The thing about blockchain that is the one thing you really need to know is that you can have somebody make a mistake and it's still safe. They can put in a stupid password. It doesn't matter. The reason it doesn't matter is a consensus thing. You have to have lots of people make the same mistake. That basically doesn't happen, okay? So it doesn't have a single point of failure. You have to get lots of people to do the same thing. for the ledger to be broken, misrepresented, cleaned, whatever, okay? So it's a very highly reliable thing for figuring out what's going on. In fact, what we do is we log things on the blockchain that include the permissions of who's allowed to do what, the questions, so the actual code that you run over data is logged there indelibly, so it cannot be changed, along with permissions. So now you know these people can do this thing with this data on that algorithm, see the code, on that, and if they do that, then this is what happens. A further thing that gets logged is often there are payments involved in that. So if I run this algorithm on my data, you give me $2.95. If I do it twice, I'll give you a discount, and it's only $5 or something. Whatever the business deal is. But it gives you a way of knowing very precisely what's done. This is important for the science, too. Because a lot of the things that are wrong with the data that we have is that we're not quite sure what algorithm was done. It was variance, but did they throw out outliers? Sometimes they do. Did they normalize it in some way first? Sometimes they do. If you don't know that, then the number you've got is something that you don't understand. And the third thing is never decrypt data ever. And this is hard to sort of understand, but if you look at the Snowden papers, right, with the NSA, the thing that's most striking after you sort of digest it all for a while, yeah, they were collecting all this stuff, but you begin to notice things that aren't in the papers. One of the things that's not in the papers is that there are no cases of them breaking strongly encrypted data. What they do is they wait for a place where people decrypt it, like to do computation on it, and then they steal it. Okay? So if you never decrypted it, it doesn't get stolen, even by people like the NSA. That's an important thing. And so you say, well, but how are we going to compute on it? I'll tell you how that works in a couple minutes. But you can actually answer most of the questions you want to ask, perhaps almost all, on encrypted data. Okay? That turns out to be legally very important. Because if I give you something that's encrypted, it doesn't violate HIPAA. It doesn't violate locality things, right? It doesn't violate ownership laws. Because it's not useful to you. It's just this bunch of ones and zeros. Okay? But there are things you can do with that, given the correct permissions, to answer questions about the aggregate. So not about the particular data. You can't do anything about particular things. But you could, for instance, look at the average success rate of something across hospitals or across doctors or across procedures. And that average is pretty interesting. And you might want to compute that, but it's a proprietary thing. It's patient data and so forth. But this gives you a way of doing that without violating those laws. So what is it? So this is the way it looks. It's a layer that you put on top of your existing databases. You don't need new databases, okay? In fact, it's good not to have new databases because you don't want everything the same. The moment you make everything the same, the bad guys can take it all, okay? So you take the old IBM 3060 or whatever, you know, and the PDP, whatever, you keep using them. It's okay. But what you do is you send questions to them, and they execute code locally behind their firewall in their own little machine language and stuff, and then they post the answers. And what that does is that means you don't copy the data around, you don't expose it, you don't have a homogeneous system that can be easily attacked, okay? And then what you get back is you get answers. The fancy way is you send the algorithm. I want to run algorithm number 236 on this data. Here's my identity credentials. Here's the permissions. You check it with the stuff that's on the blockchain. You run it. You post the answer. But you never decrypt the data because you can actually do it in a way. Let's see if I have this. Oh, I got ahead of myself. Sorry. in a way that is never decrypts the data. Anyway, so what this says basically is that the things that are on the blockchain are sort of like an operating system for your data processing. It's not a lot of data. The data is not actually on the blockchain. The data stays where it's supposed to be, like in the doctor's office or the radiology place or the testing lab or wherever, and it gets queried. And that says, oh God, this is going to be horrible, because you have, as a human, the experience of like writing pieces of paper and asking people by email for data, and it takes 5 days, and the lawyers are involved, and it's a nightmare. No, once you get things set up, it's milliseconds. So for instance, when you do a query on Google, right, you get these ads. So those ads, send out requests to everybody who makes ads, and they all bid on you, and they had a little auction, and then they sent the ad to you all in 20 milliseconds, and you don't even know it. Okay, so that type of communication is really cheap. You can just do it, right? It's not like the human experience of communication. And I'm not going to, go through this because, see, arrows, blockchains, things like that. But it's what I just said, okay? We can go through it if you want. And then the other thing is the secure multi-party computation. Now, I want to, so this sounds like magic, okay? To be able to compute things without ever decrypting them. So I'm going to do a little exercise for the audience, okay? I'm going to tell you how to compute her salary plus the average of her salary, my salary, and your salary, okay? Just to do that, without being attackable, ever. So what we're going to do is start with you, and you're going to take your salary and add a magic number to it, which you have to remember, and then give that to her. Now, she can't tell how much money you make because there's this random number added to it. You don't have to actually do this, okay? We could, but let's not. I'll just go quickly through it. But notice that you could steal the data in the middle, and it wouldn't matter, okay? You take this thing, which is encrypted. It's not his salary. Legally, it's not his salary, okay? Add your salary plus another magic number, give it to me. Now, you could see what I get. You could see both of those. You still can't tell what the salary is. I add my salary plus a magic number, give it to you. You subtract your magic number, give it to her. It's still got 2 magic numbers in it, so I could intercept it. It doesn't do anything. You subtract your magic number, it's still got 1 more magic number when it comes to me, so somebody intercepting it cannot see what my salary is. But when I get it and take off my salary, I now know the sum of the 3. Okay? And I can divide by 3, presumably, and now I know the average. Okay? Now, think about this as if you wanted to say, no, the thing that's important is you never exposed your salary. You never exposed it. Somebody could steal all the transmissions. They wouldn't know what's happening. Okay? So it was continuously encrypted. So let's take that into a more medical thing. Let's imagine we wanted to ask, how good is a particular procedure in a hospital? Well, hospitals don't really want to tell you that, right? But they could do this, and then we could find out the success rate of a procedure. Or we could do any sort of thing that you wanted to, where we were looking across an aggregate. And it doesn't have to be a big aggregate. It could be, 5, 10 sort of people. So for instance, in Boston here, we've used it to look at salary disparities between men and women. Now, nobody wants to expose that, because if they expose that themselves, they're legally liable. Right? Oh, you're a bad guy. But if you do it as an aggregate, you're not. And then you can find out something that's useful to everybody. And the same thing is true. And this is why the CTO of the US said, holy shit, this will change everything. Because it's a way to answer questions about aggregates without exposing the personal data, without endangering proprietary interests. And you can do this across jurisdictional lines where you have data locality things. So it's interesting. And we have working examples of this now. We do it with credit card data and location data and government data, but you could just as easily do it with medical data. And if you're interested, we could talk about actually doing a little example. From a technical point of view, one of the really cool things which you don't care about, is that you can cache things. You can save intermediate results. And they don't have to be protected because they're encrypted. So the way the internet works is there are little local stores of regularly used data. So when you look at a movie, you're not watching the movie from the original place. You're watching local copies. There's local copies everywhere. And they get flushed if people stop watching the movie. You can't do that with secure data or sensitive data because it has to be protected. But if it's encrypted in this sort of manner, you can have local copies, which means you can send huge amounts of data, and to the user, it will look like it's instant, right? Because they're just getting a little local copy. You don't care about that, but if you're going to have a real data sharing thing, like sharing images, sharing large amounts of stuff, you don't want to have to invest $1 bajillion. You want to do it on the existing infrastructure. This gives you the power of doing that on the existing infrastructure without slowing things down. Pretty good. So these are the people that we have that are supporting it. You know, MasterCard, Intuit does taxes, obviously, NEC, Orange. We're setting up national systems for the government of Colombia and Senegal using money from the European Union because they don't have any money themselves. And we're also doing some other things. So for instance, a couple months ago, I keynoted the European Union presidency opening. So they change president once in a while, right? So this was in Estonia. And because Estonia is really on about this sort of data system, they asked me to come and speak to all the assembled ministers. It was sort of interesting. But I was giving them roughly the political version of what you're hearing here. And they loved it because they're struggling with privacy regulation. It's called GDPR. So all data now in Europe has to obey things that look a lot like HIPAA. I mean, it's not exactly like HIPAA, but it's a lot like it. And they have data localization. They have all these countries, but you can't share data between countries. So, you know, the obvious thing is you know, you've got an autonomous car drives from Germany into France, and it immediately crashes because you can't take the data from Germany into France. What are we going to do? Right, OK. So this actually addresses that problem. And that's why they're paying for trials, you know, prototype systems in places like Senegal and Colombia. Another one is in China, where, surprisingly, perhaps, they have similar very concerns. They're worried about company data exploiting citizens. They're also worried about how do they coexist in a worldwide data environment. You know, to be successful nowadays, you have to move data across borders. China has their great firewall. They're concerned about things. Other people don't want various other things to happen out of China. How do they address this? So I think this may be a way to do it. So we're going to set up a demo between China and another country called Hong Kong. Yeah, OK. Legally, it's a different country. OK. Anyway, and you can, oh, sorry, I don't know if I put that up there. So this is trust.mit.edu if you want to see it. So just, I thought I would go a little bit further with this and not do it in too much detail. But look, you know, there are ways that you could very easily apply this to medical data. This is the part that I have been on about for quite a while. I think it was interesting for me to hear the panel, the last panel. So one of the things that we set up in New York, which we're not quite sure is going to happen because of funding problems, but we set up a study that is 10,000 people, a demographically accurate sample of New York City, where we're going to follow people's movement, socialization, criminal record, employment record, payments, oh yeah, medical data, genome, what their kids do. We're sewing little Bluetooth sensors in the kids' underwear. Well, because how often do the kids spend time with the parents? It's actually sort of an interesting question, right? Different styles of parenting, things like that. And the idea is to do that for 30 years. And what you do is you collect a very different type of data than what you're used for, because this is not administrative payments data. This is behavior data. And it's not sickness data, it's health data. So this is before people get sick. What lifestyles result in what outcomes? Right? Which you don't know, and I don't know. And I think it's sort of crazy that, is milk good for you? I'd sort of like to know, right? You don't get a clinical trial on that because nobody's going to make a lot of money off of it, but I would really like to know that. So the way you do that is you do a population study for a long time, and you say, well, these people drink a lot of milk and they don't do so good, and these people do. Same thing with aspirin and many other sorts of things. And so in this model, what happens is people collect data for themselves. It's very different. So we set up a repository. You sign up. You collect everything about you, but you own that data, okay? And then I come along as the study person and say, but I'd like to ask some questions. Would you like to answer? And if you say yes, we flick the switch and we get the answer. Think about that compared to the normal study thing. So in the thing I just said, you do an IRB, but remember the IRB is going to be a very standard thing. It says people who have opted into this study for the last N years typically answer questions like this in this way, and they've done it 422 times so far, and we're going to ask this other question now in the same format. That's a really easy IRB application, right? Okay? And when they come back to you and say, yes, go ahead, then you just flick the switch. And then later that day, you have the answer to your study question. Think about that. I mean, you all know, like, none of this, like, recruiting the people and getting it, it's like, so it could be very much faster. And the point that I never quite understand is why don't pharma companies do this? Because it would be billions of dollars if they could accelerate the rate of drug approval using something like this. And the key is you have to trust that people will say yes. You have to use sophisticated statistics to be able to get nice matched samples, right? But we have that math, okay? And what you get for that is you get this thing that lets you answer lots of different questions, but it really accelerates the process of asking questions. And incidentally, something that's near and dear to my heart, most of the things that we ask, there are other sorts of effects going on that we don't expect. We're not all that omnipotent, okay? And so we don't have a good way of discovering, for instance, drug interactions. We don't have a good way of discovering interactions between treatments and how you raise kids. I'm just making that up. But there's a bunch of things that we don't expect necessarily that might turn out to be pretty interesting. A real fishing trip, right? But in this sort of framework, you can do fishing trips a lot easier because the data's already there. The people are willing to go along with it. All you need is a little bit of evidence that this is a reasonable hypothesis, and then you should be able to do it. I think that makes a big difference. And this is the most recent thing that's a version of exactly the same set of thinking. They would call it Tradecoin because we're talking about money here, but it could be anything. It's basically a way of taking diverse assets and monetizing them or securitizing them. That's finance, right? What's that have to do with medicine? Well, let's imagine that you had a whole bunch of people that had genome data, and you wanted to put that together into a large database. Okay, that's difficult because they own it, it's got privacy, blah, blah, blah. But what I've just told you is a way of actually doing that, where you can then allocate anything that is income back to the holders of the data proportional to the value of that data to the question in a very sort of clean way. If you had the critical data, you'd get most of the return. If your data happened to be irrelevant to this question, we can calculate how much your data contributed to the solution. So it's a really interesting way of combining lots of small things So you could, again, have hospitals put their data together. Individually, they're not compelling. If you can get 10,000 of them, you can do some really important things. But of course, they're going to want value for that. But this gives you a way to say, well, your data, did this much of the variance in this question. And therefore, if there's a revenue stream, you get this much back, right? And the key here, this is not rocket science again, but the key here is this way of being able to take distributed data, and rather than sticking it in one place, keeping it federated, but knowing exactly what's happening between the data by logging it so that you can audit it, and making sure that it's safe along the way. Right? So that's the bottom line. Let's see, we can do this, da-da-da. You don't want to know that. There are some books. We made some books because our papers are scattered over a huge literature. Most of the stuff I just talked about is in the Trust Data book. It's like $12 on Amazon. We sell it at cost, basically. So if you're interested in a little bit of a nerd, feel free. And there you are. Thank you.
You've done very well. We have time for maybe one brilliant, insightful question. Anyone courageous enough to do that? Well, then we'll thank Sandy. And isn't it fantastic here at MIT, the kind of resources that we can draw on? And you did make it fun. Congratulations.
Good. Well, I tried.
Can we keep the clicker, though? Thanks.